Hi folks, we're doing section 4.3 in our homework today. Let's take a few notes. Let's go through and look at it. So here we go. Section 4.3, connecting first derivative and second derivative with the graph of it. So we're going to do a little review here. Factor the expression, use sign charts. So I'm going to put the answers up there. Now how do we get that answer? We need to factor it. And your two answers are positive 3 and negative 3. So what happens when your answer is less than negative 3, like negative 4? Well, then we're going to make a sign chart. If you pick a number less than negative 3, it's going to be positive. So I got a plus sign there. At negative 3, it's 0. Between negative 3 and positive 3, it's going to be negative. We could put a 0 in there to find out exactly what it is. And then 3 at 0. And what if you got a number that's bigger than 3? It's going to be positive. So you got positive, negative, and positive again. Okay, let's try number 2. Let's factor it. You get 3 answers there. 0, negative 2, and 2. So those are our points that we're going to use. So what happens to the left of negative 2? Like negative 3. If you put a negative 3 in there, it's going to be negative. At negative 2 at 0, between negative 2 and 0, my answer is going to be positive, and that's what we want to find out. From negative 2 to 0, that's where it's positive, greater than 0. From 0 to 2, it's negative, and anything greater than 2 is positive again. Okay, try number 3. Find the domain of the function and the derivative. Well, we can do everything. So on number 3, all real numbers, and if we do the derivative of it, it's going to look like that. E to the x is always positive. And 1 minus x, that's okay. We could put any number in there and it works out. We're looking for things that do not exist. Okay. Number 4, we can put any number we want to into the original function, but when you do the derivative, it cannot be 0 because then you would be dividing by 0. So that's no good. Number 5, all real numbers are all numbers except where x equals 2 because you're dividing by 0 there. Same with the first derivative. You can see it. X minus 2, the quantity squared, by using the quotient rule. And for on the bottom there, we had the same thing. And number 6 is just like number 4 in terms of finding the domain of the function and the derivative. So here's what we're going to learn. Intervals were the decreases and decreases. First and second derivative tests. Where is it concave up, concave down? Points of inflection. All of this deals with calculus. All of this deals with not being able to use your graphing calculators. So when we have a quiz and test, we'll have parts of the quiz or test where you can use your calculators, and there'll be parts where you cannot. So you can't just graph it to be able to go through and look at it. Okay. So what's happening with our derivative? Here's our function. Okay. At A is our left-hand point. That looks like an absolute min there. And then between A and C1, our derivative is greater than 0 or it's increasing. At C1, the derivative is 0. And then between C1 and C2, it's also increasing because it's going uphill. Then we have a local max at C2. Between C2 and C3, the first derivative is less than 0 or negative. Then we have a local min. Our derivative is equal to 0 there. And then between C3 and C4, it's increasing, so our first derivative is greater than 0. At C4, it's a max, but the derivative is undefined because it's a sharp corner there. Between C4 and C5, it's negative. The derivative is negative because it's going downhill. Then we have a derivative equal to 0, and then we have a derivative being less than 0, and then we end up with our local min at the very end there. Be able to go through and do it. Okay, so let's take a look. So at a critical point C, let's take a look at what happens. If our derivative is greater than 0, we're going uphill. Then we have a local max, the derivative is 0, and then we have the derivative being less than 0 or negative. So that's why we have a local max there. Same thing on here. except our lines are curved a little bit differently. First derivative is increasing. Here it doesn't exist, that's a sharp corner. And then after that, it's decreasing. So our first derivative is less than 0. That's the first derivative test for local extrema. We can do the same thing with the mins. It's very similar. No difference there. Now, what happens if it's increasing? If it's 0 and it's increasing. Okay, there's no extrema there. We don't hit a hilltop or a valley. Same thing if it's decreasing everywhere, but here it doesn't exist because that would be a sharp corner. So it doesn't work that way. Same thing here. If you're at A and you go after that, to the right of that, your first derivative is less than 0 or negative, then you have a local max. Conversely, same thing if you have a local min. It's all dealing with the first derivative. Same thing if we've got mins. Not much difference there. So, do we know where the local extreme values are for this one? Well, let's go through and find the derivative. Set it equals 0, and it looks like you've got positive 3 and negative 3. So what happens to the left of negative 3? What happens to the right of negative 3? What happens at something that's to the right of x equals 4? So we have a local max at negative 3 because we put that number into our function. This isn't new. We did this last time to find your local mins and local maxes. Okay. And the range is from negative infinity to positive infinity. We don't have any absolute extremas. We have relative mins and relative maxes. There's the graph. I'll remove my picture. So there's verification. Now remember, up until that time, we couldn't use, or we didn't want to use a graphing calculator. So we can actually go through and figure out exactly kind of what it looks like with local mins and local maxes. And we'll go through and do this. So then we talk about concavity. It's concave up when it's increasing, but it could be concave down. Concave up looks like it's caved upwards. Concave down looks like it's caved downwards. It's not a straight line then. So we can be able to go through and do that. So here's a good example of what concave down looks like. Notice they're both increasing from left to right, but the concavity changes on each one of those.